Okay, so this is booklet 5 of the Year 11 chemistry booklet, and I'm scrolling all the way down to page 5. So empirical formula. So have a read of this page, but the empirical formula basically it's the formula where you have the lowest number of mole ratios of the elements in the compound. So the simplest whole number ratio of atoms as well. So let's look at the examples. You can have a read of the page 5. I'm going to do the examples. I want to do the first 2 examples on page 6. Okay, so the first question says a compound of hydrogen and oxygen is analyzed. That's really important. We've got hydrogen, not hydrogen, oxygen, hydrogen and carbon, Compound of hydrogen and carbon is analyzed and consists of 75% mass of carbon and 25% mass of hydrogen. So, determine the empirical formula of the hydrocarbon. Okay, so we have carbon and we have hydrogen. And we don't have anything else. I'm going to draw this up in a table. So carbon and we have hydrogen. How much do we have of each? Well, we have 75%. Let's go back to the page. Just moved around a bit. We have 75% of carbon, 25% of hydrogen. Now you notice I didn't put the percentage. I'm going to change that to grams. Now the reason why I can change that to grams is because I'm going to assume we have 100 grams of sample. So if we have 100 grams of sample, these 2 percentages can change to grams. So whenever you have percentages, you can change it to grams. So that is mass. We need to convert that to number of moles. So if you remember, N equals mass divided by molar mass. We're going to be using this quite a bit. So the number of moles of carbon is the mass, so 75 divided by the molar mass of carbon, which is 12. We got that 12 from the periodic table. So if we work that out, 75 divided by 12 gives us 6.25. 25 mole. And on the other side, the number of hydrogens is just 25 divided by 1. So that'll give us 25 mole. Now what you do is you've got these 2 numbers here. You've got 6.25 mole. I just didn't have room to write mole in there. And we have 25 mole. What you need to do is you take the smallest number that you have, so the smallest number of mole, which is 6.25, and you divide all the other moles you have, in this case it's just 25, by the smallest number. So 6.25 divided by 6.25 is 1. 25 divided by 6.25 is 4. So that tells us the ratio 1 to 4. So we have 1 carbon and 4 hydrogens. So 1 carbon, you put the 1 there if you want, but I'm not going to write it. And 4 hydrogens. So it's CH4, which is methane. All right, let's do the next one. Question 2. And I might actually just make a bit more room here. Okay, so question 2. A student oxidizes a weighed sample of magnesium in excess air to produce a white powder, magnesium oxide. If the original sample of magnesium weighs 1.204 grams and the magnesium oxide produced has a mass of 1.996 grams, determine the empirical formula of magnesium oxide. We could probably do this because we know what magnesium oxide is, but we need to let's work it out using this the information we have. So a student oxidizes. That's actually really important. So oxidizes mean oxygen and it's available, and of course to get magnesium oxide from magnesium you have to have oxygen. So let's write down the information we have. We know, first of all, so we'll draw up this table. What do we have? We have magnesium in our sample, and the mass is 1.204 grams. Now in this case we don't have percentages, we're automatically given it in grams. So 1.204. What else do we need to make magnesium oxide? We need oxygen, hence magnesium oxide. But we don't know how much oxygen we have. How do we work that out? Well, the magnesium oxide produced has a mass of 1.996 grams. The mass of magnesium is 1.204 grams. So the rest must be the oxygen. So that will tell us the mass of oxygen we have. So 1.996 minus 1.204. That gives us 0.792 grams of oxygen. So we put that up there in our table. So 0.792 grams. So we're effectively at this step, okay, from the previous question. All right, so we've got the mass. Once we've got the mass, we convert it to a number of mole. N equals mass divided by molar mass. So the mass divided by the molar mass. N equals the mass divided by the molar mass for oxygen. It is 16. That's just getting it from the periodic table. For magnesium, we look at the periodic table, it's 24.3. And what do we get? So 1.209 divided by 24.3, we get 0.049, blah, 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 mole. The other one, we get 0.792 divided by 16, we get 0.0495 mole. Units of mole, yep. So these are our 2 moles. I just didn't have room to write the units, but you should write mole. So we take the smallest one. Well, they're basically the same number, yeah? You know, slightly off, but they're pretty close. So if you, whichever one you take, and you divide by each other, you get 1-to-1 ratio. So the last line tells you the ratio. So you take the smallest one, in which case it doesn't matter which one, and you divide them by each other, you get 1-to-1 ratio. So the empirical formula is Mg101, but as we know, we don't write the ones, so it is just MgO. That's it. Okay, you can never go at question 3. Okay, so let's go down. Let's have a look at molecular formula now. Okay, so we just looked at empirical formula. That's the simplest ratio. Molecular formula is a multiple of that, some type of some form. So we look at CH2 for ethene. The molecular formula is C2H6. The molecular formula tells you the actual number of atoms. So if you use the molecular formula, you can actually draw the structure. There are some things like water where the molecular formula and the molecular formula and the empirical formula are exactly the same. So the ratio is 1-to-1. In this case, with ethane, the molecular formula is double that of the empirical formula. You can see the carbons times by 2, the hydrogens times by 2. So I'm going to stop the video here, and I will make another video to go through the question 1 and question 2 on page 9.